So we're going to keep doing examples for three-dimensional linear vector value functions. This time we want to find the equation for the line TR that's parallel, there's a keyword, to W, which is 2I minus j plus k, but it goes through the point 287. All right, well, first off, we need a direction. Now, because it's parallel, our new vector will have a direction vector that is the same because it's parallel. So that means our direction vector is the same as W. It's 2, I'm just going to write it in bracket notation. I can't help myself. It's 2, negative 1, 1. Right? It's the same because it's parallel. Parallel is really easy. So then OR, I'm just going to vectorize that point. It's 2, 8, 7. Okay, so R of t would be, you take your direction vector 2, negative 1, 1, you multiply it by t, and then you add OR, which is 2, 8, 7. So that gets us 2t plus 2, negative t plus 8, and t plus 7. Easy as that. All right, so parallel is really easy because the direction vector is the same as the vector you had. Orthogonal, however, well, that's going to be a little stickier. So we want to find an equation of a line that's orthogonal to the lines A, B, and TR from the previous examples. The orthogonal line must contain the point 1, 2, 3. Okay, so let me just remind ourselves, AB, I have to go back a page and find AB. AB was, well, or had a direction, that's what we really care about, of negative 3, 4, negative 3. So let me put it this way. The direction vector for AB was negative 3, 4, negative 3. And then the direction vector for TR was the same as what we had up here. It's 2, negative 1, 1. Okay. So how do we get a vector, a third vector, that is orthogonal to two known vectors? The cross product. Yes, we will need the cross product. So recall, I'm just going to put a little note in here. The cross product, if I could spell it correctly, is always orthogonal to two distinct vectors. I say distinct because, of course, the cross product doesn't work if this vector was a multiple of that vector, then it wouldn't work, right? But that's not the case here, so we're fine, right? So if they're really the same vector, that doesn't really help. But other than that, we would be fine, and this is fine. So we are going to find the cross product. So our direction vector, V, right, dir for direction, will be the cross product. So I'm going to take I, j, k, and I'm going to cross product these two. It doesn't really matter which order you put them in. I'm just going to put them in this order. It doesn't make any difference because this is just orthogonal. Remember, if you go the other way, right-hand rule. So the right-hand rule means that if I go one direction, it's pointing one way. If I flip them, then it just points the other direction, right? Okay, so let's see here. I, j, k. So it'd be 3i minus 3j plus 8k. Take away. And then we're going to go the reverse direction. 3k, 4i, and negative 6j. Okay, so that would be 3i take away 4i is negative I. Negative 3j minus a minus 6j is plus 3j. 8k take away 3k is plus 5k. There's our cross product. Or if we want to write it in bracket notation, negative 1, 3, 5. So this is our direction vector for our new vector. I'm just going to put that symbol for orthogonal. Right? It's our new orthogonal vector, our new perpendicular vector if it was 2 dimensions, but we're 3 dimensions, so it's orthogonal. Okay, so r of t, our new vector, will be that new direction, negative 1, 3, 5 times t plus, all right, I need to vectorize, if you will, my point. So it'll be 1, 2, 3. So this is OP, would be 1, 2, 3. So that's where that's coming from. You turn your point into a vector. And then again, this is perfectly fine. You can write it that way, but it tends not to be the way we write it. So negative t plus 1, 3t plus 2, 5t plus 3.